All right, recording has started. So let's get going. Welcome to our monthly Ask an Expert session this month using oneAPI with FPGAs. My name is Steve. I will be your moderator, and I'll be back in a moment with more information about how that will work. But I first wanted to introduce your experts for today. First is Riri. She is a member of our PSG technical training team. She's on my team. We're both in the technical training department. And she is our subject matter expert on oneAPI and has taught hundreds of engineers through workshops and conferences on using oneAPI with our devices. Our other expert on the line today is Duncan McKay. He is the product manager for the Intel HLS tools, including oneAPI, DSP Builder, and the HLS compiler. He has 25 years experience and has been evangelizing HLS for a long time. You can see some of his other credits there um, with HLS. So he will be a great resource for additional questions. So with the introductions out of the way, if you have any questions at any point during the session, you have two ways to ask. You can either ask over the phone or you can ask in the chat. I will be monitoring the chat separately so that the experts can continue answering questions and presenting. So please feel free to enter questions at any time and I will forward them on to the experts. And of course, if you do want to ask over the phone, please feel free to just unmute yourself and you can raise your hand or whatever, and you can ask your question that way. So with that, let's get started. Oh, some ground rules, first of all. Any questions that you may have are fair game over the phone or in the chat. If it's a detailed design-specific question, the experts will try to answer if possible based on your description, and we want to answer as many questions as possible. If you're asking something that's quite complicated, we'll try to get an answer to you, or we might want to follow up with you after the session, and we can do that. And we may even point you to your local FAE if you need further assistance beyond that. Okay, with that out of the way, let's get started. So Riri, it's over to you.
Thank you very much, Steve. So welcome once more, everyone, to today's Ask an Expert session. So today on our agenda, we would run through what oneAPI really is, especially for FPGAs, to kind of give us like an introduction to the tool itself. And then we'll kind of brainstorm through how to get started with the product. And then we'll head over to DevCloud so you could kind of have a feel of what it actually feels like using oneAPI on FPGAs. And of course, lots of questions. So with that, great. Okay, so what is oneAPI in the context of FPGAs? This would lead me to answer the question or talk about this trending heterogeneous computing that we have out there. So as we are well aware, there's diverse workloads, with the influx of with the growth of technology, there's so much to do, and honestly, one architecture cannot necessarily fit into all of these workloads. So of course, that is driving the fact that we need to use diverse architectures for these diverse workloads. So eventually you're talking heterogeneous computing. So at the end of the day, we're trying to combine the strengths of individual architectures, such as their performance, their throughput, their latency, architecture, memory bandwidth, and so on. We're trying to combine all of that and put into one overall system, such that we have a heterogeneous system that could actually, attend to diverse workloads, whatever those workloads may be. Next slide, please. But as simple and as beautiful or as illuminating as that sounds, it has its own challenges, right? So you can't just up and pick different architectures combined for different workloads. You have to get through the software development complexity that is involved in using each of these architectures. So at the end of the day, you find that you're needing to maybe train engineers to be good in one architecture or good in all of the architectures, I mean. And then you can't just use one model. You have to create like different programming models, and that would also require using different tool chains. So be it vector architecture, spatial, or matrix, you're having to use this bunch of different tools, which at the end of the day kind of increases the time you take to develop something, to develop a design and put it out there. So this is what oneAPI is trying to address. Next slide, please. Yeah, so with oneAPI, we're saying there is one model that fits everything. So think of it as one shoe for all of your problems. So you have this great product that is a unified programming model. It gives you a unified programming model that can target diverse architectures, be it CPU, GPU, FPGAs, AI. One API itself can give you a common developer experience across all of these architectures. So at the end of the day, you're not having to compromise between one or the other, and then your software complexity is greatly reduced because you are having to use one model for everything. And of course, it's industry standard and there are open specifications. So it's really this beautiful tool there that sort of really helps with heterogeneous computing, gives you that flexibility to use as much architectures as you want to achieve your desired diverse workloads and programming. So when it comes to FPGA, next slide, please. When it comes to FPGAs, the oneAPI tool that is involved is okay. So generally, let me talk about oneAPI itself. This product has it requires first a direct programming where we use that third parallel C++, and then for the API-based programming is based on a bunch of libraries that we have there, and then of course there's analysis and debug tools to help you in the process of your development. So all of this Intel has provided as the oneAPI product itself. But when it comes to FPGA specifically, what you're interested in or what the oneAPI product is just it's the combination of the language itself, which is data parallel C++, and the analysis and debug tools you would require to sort of debug through your program or your model, as the case may be. Next slide, please. So the programming language itself is data parallel C++. Think of it as C++. It's more like SQL with a bunch of extensions. So there's really not much of a difference between using C++ and DPC++. It's just more enhanced, and it's industry standard as well. And this is our own adaptation of SQL itself. Next slide, please. Yeah. So when you intend to finally get started with oneAPI, for FPGA, the product offering you'd need is the oneAPI based toolkit. So this can get you through the first two steps in development for FPGA architecture. But if you want to go and actually put it on the hardware, then you'll be requiring the Intel FPGA add-on for the oneAPI based toolkit, which currently what it involves is first grabbing the FPGA platform and the board support package. Now you need a board support package because you're not going to be working with just a standalone FPGA. You have like a bunch of other peripherals on the FPGA, so hence you'll be actually using the board. So the BSP kind of takes charge of all of that communication between the FPGA and those other peripherals. And now this is provided through third-party vendors. So when you grab the FPGA platform and the BSP, that's the corresponding software you're working with, then you come back to sort of pick up the quarters version or that you would require for that particular board that you are targeting. So on our website, we have information on what quarters version is required for what particular board you are targeting. So this put together makes up the FPGA add-on. And then remember I said you can walk away with just using the oneAPI based toolkit, which will take you to the first two stages of development. We're going to look at those stages of development shortly. But then when you want to actually target the hardware, you'll be needing to grab a board support package as well as the Intel Quartus Prime Pro software. And all of this is for Linux machines. Next slide, please. Okay, so how do I get started? Good question. Now you need to know the language DPC++. If it's something you're not familiar with in the past, I think if you're maybe used OpenCL at some point it will not be strange to you. But if something you're not completely familiar with, or you just want to brush up on it, we have a bunch of Jupyter notebooks on the Intel DevCloud that can walk you through DPC++ itself. So there are different modules. You can go on the DevCloud, get your hands dirty, dive into this tutorials, and start learning on the go. Next slide, please. Now, if you are more of a book person, we have a free ebook available on Amazon and on Springer. The version on Amazon is actually the Kindle version. You can get the PDF on Springer. So it's a data parallel C++, and it kind of walks you through, like enough to get you started to write a DPC++ program. It was written by a bunch of Intel engineers and put together for really specifically for your use. So yes, so you have the book version available. The book method of kind of getting familiar with DPC++, as well as going through tutorials. So now let's say you've gotten DPC++ out of the way. Next slide, please. Yeah, now you want to use it with FPGAs. So you could, attempt self-learning, and that would involve taking a copy of of some of our documentations, such as the programming guide and the optimization guide. Now with these two, you can pretty much read your way through it and start learning on your own how to use oneAPI with Intel FPGAs. Next slide. Okay, but again, you can also, get your hands dirty by just diving into the GitHub we have, which has a full range of tutorials on DPC++ with FPGAs, and you would have so many, tutorials actually out there inside of this GitHub, and it also comes with a download of your of the oneAPI based toolkit. So when you download oneAPI based toolkit, you're going to have this bunch of tutorials in there that would actually help you also in getting started. All of this also involves self-learning, sort of. Next slide, please. Okay, and another great way to also be a part or get started or learn about this product is to register for our workshop, which we kind of do every quarter. I know the next one is coming up in about, I think, next week actually. So it's 3 hours workshop, and you would actually walk through introduction of oneAPI product itself, and then we'll look at the toolkit. Then we'll actually touch on some of the optimization techniques you can use to make your DPC++ program really fit into the FPGA and get really great and awesome performance. So registration link will be included in your thank you email and also in the chat window if you're interested in registering for that instructor-led workshop. Okay, next slide, please. Okay, so again, there's actually an easy way through Intel DevCloud. Now, if you go to the Intel DevCloud, which I'll be showing you a demo of shortly, you can sign up for free. You have access to, to it for free. It's for, I think, about 3 months at first, and then you just need to send an email that you want it extended, and it's also going to be extended for free as well. And you have access to all of those all of the all of the oneAPI products already embedded in there for you, so you can actually just get started and begin to learn on the fly. So without having to actually download the oneAPI based toolkit or get an FPGA add-on, you can do all of the learning stuff out of the way through using our Intel DevCloud. Next slide, please.
Riri, there's a question in the chat. Do
Okay.
the examples and tutorials target any specific board for the hardware that people will use for this?
Oh yes, the tutorial. I think it's usually quite stated there. I believe it's the area 10 most of the times that it targets in our tutorials when you're on GitHub, because you'd have to grab a node in the DevCloud for that. So yes, you have it targeted to a specific board when you get to that point of actually deploying on a board. Yeah. But you don't need to have the physical board. Yeah, on the DevCloud, it's already like connected in there for you to use. Okay, next slide. Okay, so again, if you'd rather just do things on your own, you can go ahead to download the tools yourself. So you want to first of all start by downloading the oneAPI base toolkit. There's a reason it's the base, because without it, you can't really go and do anything extra. So in the development stages, when it comes to using oneAPI and FPGAs, there are 3 stages. The first is the emulation. And next is optimization report generation. And then finally is the full compile, which would be on the hardware. So the first 2 stages, you can get away with doing that on the oneAPI based toolkit. You don't need the FPGA add-on for that. So if you download that tool, you would, pretty much be able to perform emulation and also generate a report, which will kind of give you an idea of what you need to tweak or where the bottlenecks are lying, where the bottlenecks are in your model, what you need to change, before you actually get to do a full compile. Now, when you're ready to run on the board, then you want to download the FPGA add-on for oneAPI-based toolkit. So that would require you grabbing the BSPs and the boards, which are provided through our third-party vendors, and also downloading the Intel Portus Prime software version, and making sure you have the right OS, which would all depend on the board that you're targeting. So on our side, we have like, I think a table which kind of highlights what board, what version of Portus is required for whatever board you're looking at to target, and then a link to the third-party vendor for you to grab that particular FPGA platform. So yeah, that's if you want to do it on your own. But I would suggest, try the easy way out first. Just do everything on the DevCloud, and then when you're truly ready to start on your own, then you can go through this route. Next slide, please. I think the next slide is for us to go to a demo. Yeah, exactly. I was right. Okay, so.
And I just put the tool link in the chat for you too.
Okay, thank you so much. So let me open to the DevCloud and share my screen.
Let me stop sharing.
All right, so I have it saying I'm presenting. I hope that's true. Okay,
yes. So
to get started, you want to come to the DevCloud page and actually sign in. So right now I'm signed out right here, which is okay. So you want to sign in or create a new account. But before we do that, let me quickly take us to, so how it would look like for you as a new user. So this is what you would see. Oh, well, it's same thing anyway. So this will take you here. And then if you do not have an account, you want to sign in actually, or create a new account. I'm sorry. You want to create a new account. I am signed, I have an account and I'm signing in. So this is what it's popping up on mine. But then you'd have like a bunch of forms, which it kind of, you just put your basic information, your name, stuff, and all of that, and then you're good to go. Then it's you get an email that you need to provision your account, and so once you click on that link, you're pretty much ready to start to dive into programming. Now, when you're done, you want to come to the Get Started page, the Get Started link, and then when you do that, you want to launch the Jupyter Lab. So launching this will take you to Jupyter Lab, which pretty much has like a bunch of tutorials in there that are oneAPI related. So for this demo, I'm just going to be walking through FPGA, a short training. We use it during our during our workshops. So we have that here. Let me just come here. I have that open here. Good. So to begin, I'll just walk us through like the steps involved in development when we are using oneAPI for FPGAs. So there are basically 3 steps that I mentioned earlier. So this is how the development flow looks like. First, you've pretty much prepared your DPC++ code programming model, which in it you've created kernels that are going to be targeting the FPGAs. When you've done that, you want to actually check to be sure that everything works as you want it to. So that's some sort of functional validation that you want to perform. So this typically takes seconds to compile, and what the compiler does is kind of create an early image for you for that particular device you're targeting. So it creates an FPGA, an early image while using your CPU to do that, right? Or whatever device is your host device. Now, after you're satisfied that your functional validation has passed, you want to now generate reports. So that's like generating the static reports. Now, typically this would take minutes. I think the longest it can go is about 20 minutes, depending on how big of a design you have. But then, I mean, minutes is nothing compared to the hours a full compile will take you. But then it's doing all of this because it's not just creating an early image, just kind of creating like all of those connect when it comes to actually targeting the hardware itself. So it's going to provide you a report, usually in a HTML version, where you can look at the report. It will show you the bottlenecks. It will tell you, okay, you have issues with your loops, you have issues with throughput, you're not meeting the II that is suitable for your design and all that stuff. And it will even, do some sort of dynamic referencing to what part of your code is actually giving you these problems, and could make suggestions on how best to make your work a lot more optimum, right? So after you've gone through the report painstakingly and you're satisfied and you've gone back to kind of tweak some stuff in your code, you will go back again to perform emulation, make sure that everything is functionally correct, and then again generate reports and see whether whatever changes you've done has been made and actually is giving you the desired result you are looking for. And then when you're now satisfied with these steps over and over and over again, you're satisfied with them, you can now come to your full compile and perform hardware profiling if you want together with that. Now, this will take hours to complete. So in a way, when you look at the development flow, you'd see why it's very important to sort of do the first two and not skip to the last. Because imagine you start a full compile that would take hours, and I mean, your code is not necessarily functionally correct. That's a lot of time you've wasted doing that. So the flow really is one to always stick to when you begin to work with oneAPI for Intel FPGAs. So here we just have the anatomy of the compilation command. So in here, we're targeting for emulation. Okay, well, here is where we're targeting for emulation, but this just gives you like an overview of what the compilation command looks like, depending on whether you're performing emulation or you're generating a report or you're doing a full compile. So I think I'll just run us through the first two and let's see what happens. So here we have our DPC++ code. I'm not going to talk much about it, but this just gives you an idea of a model we have here. And in this model, the code is just implementing a simple cumulative sum on an array of values. So all of this is done. We are simply going to create that file, and we're going to perform compilation. So for us to perform compilation, we use the dpcpp command for that. And in here, we're telling it that we are targeting the emulator itself. So we run this, and it's going to create a .mu file for us, which when we run will tell us whether or not we have our functional validation passed, right? So this is just going to take a short while, and we should be good. Good, it's done. Compile is finished, and yeah, so it says the results are correct. So yeah, so with this has kind of given us assurance that we are good to go when it comes to functional validity of our design. So keep in mind again that all of this was run on the x86 host as an emulator. So it's not using an FPGA per se for this, right? Now, to go further, We're now going to stage 2, which is where we want to, generate a report, optimization report. So in here, think about, you're trying to find where the bottlenecks are inside of your design, right? So here it's going to generate for us a HTML file, like I said previously, and in that file, you can look at the report and see information about your memory performance, data flow, bottlenecks inside of your design. You will get some suggestions on what you can do to resolve those bottlenecks. You would also get things like area and timing estimates of your design. So in here, we have a hoof transform inside of this particular DPC++ model we want to run. So it's the hoof transform is really a computer algorithm that kind of transforms pixels into lines. And it's usually used in edge detection. So when we come, this is the command to kind of target creating our optimization reports. It's going to compile to an early image. Let's look at it. So this is the file we want to use for that, the hoof transform file. We compile, and then, we create a file, and then we are now trying to compile. So we're waiting for it to compile. So all of this, like I said, takes minutes. The first one kind of took seconds. So the second stage would take minutes, depending on how complex your design is. It could take as much as 20 minutes, but this wouldn't take up to 20 minutes. I think it'd take about, if it's long, maybe 5 minutes. But yeah, anyways. Okay, so we're still waiting. Good. The compile is finished. So with that, we can now look at what it has generated, which is the report. So it generated a report which shows up in here. It's going to show up here. We have a project file, I think. Let me quickly link us to that part. Okay. See, hold on. Okay, so in here is the one I have already zipped, but I actually want to link us to where the actual file is. So let's see. Yeah, so transform. No, not here. Yeah, so it has created this project folder, and in there you're going to have the reports. So here is the report, and this is the report.html file. But if we open it here, we're really not going to be able to see anything in the Jupyter Lab. So what we like doing, or what we suggest to do, is to create a zipped version, and then so we can download locally to our machine. And then a zipped report file will appear in the file browser menu. So here you have that report.zip is going to show up here. And then after that, we can now, download it to our machine and then view it. So, but then here I have a snapshot of some part of the report for you to see how it looks like. So inside of this, we have, summary, views, throughput analysis, area analysis. So inside of the views, you could, look at specific things like loops, memory, and so on. So this is usually how the report would look like. It will have the DPC++ code for your design show up. And then if you're having trouble, it will kind of like, dynamically reference what part of the code has problems. So in this report now, we're going to navigate to the loop analysis section. And in here, we have the loop analysis section. We're having that we've got a bunch of kernels, and we can see from the kernels whether it's pipeline, what the scheduled II is. II is initiation interval, and the max frequency, what the latency looks like, and a bunch of other interesting things that you would need, right? Now, if you take a look at this report, you'd see that for this kernel B5, we're having 233 as an II. Usually you want it to be 1. 1 is the least you can get, and you want it to be 1 because really what this means is there's a build up, or there's like a very data is not flowing as efficiently as you want through the pipelines, right? And so of course this will affect performance. So inside the brief info column, you see that it's screaming to you that memory dependency is really what is responsible for this problem, right? So it has given you an idea of what the problem is, what block is responsible for it, right? So it's now up to you to kind of try and go back and say, okay, is there any way I could write my code such that the compiler is able to optimize for memory, right? So that's what the next part of this lab is going to try to do, right? So we're going to try to see how we can actually redo this such that we're going to have a better II performance. So again, we compile. We already have a file that has the improved what's it called? It has the improved DPC++ model, and with that, we want to now perform our compilation for that again, and then see what it looks like when we have done all of that. So when we do that, we can create a report again if we want. I mean, no, we actually need to. Sorry, this would create a report. While in here, we're just zipping the report file so we can view it on our local machine. But after all said and done, we've compiled. Now we have that our kernel is now, our II is now in a better place. We're not having that to be 1, which is what we actually want. So that's how working through optimization looks like. So you look at your report, you see the bottlenecks, you go back, you try to write your code such that your compiler can optimize for whatever it is you're trying to optimize for, and then you compile again to generate a report to see that, oh, this worked and this didn't work. So, and then finally you want to do the full compile, which will take hours. So we're not necessarily going to dive into that. But then in the DevCloud, before you do that, you need to grab a full compile node. You need to grab a node like that. So you have to do something extra, right? And then after doing that, you're going to have it now run the kernel on that particular FPGA. So for this design, we're targeting the area 10, and it's going to create for us the files that we would eventually check to see if everything has worked perfectly. So really that's a rundown of what it looks like when you're using oneAPI product with our FPGA device. So I think with that, we've come to the end of the demo. So yeah, questions can come in. Yeah.
Of course, please post your questions in the chat, or you can unmute yourself and ask a question. We have some questions. Oh, let me share my desktop again here. So we have some questions that came in ahead of time that we'll be asking as well. But of course, if you have any questions, please feel free to ask. All right. So some questions we got ahead of time. Let's see. How can I tell that for Riri and Duncan, of course, how can I tell that a board is supported for use with oneAPI? Can I use my own board?
Not exactly use it. Okay, Duncan, do you want to?
I can take that. Yeah.
Okay,
first
cool.
of all, for the supported boards, as Riri said, go to the Intel FPGA add-on page, and there you will find a list of all the boards that are supported for use with API. If you wish to develop your own board, or you can use your own board, you can. It has to be OFS compliant, and I'm not sure of the exact details. You need to go look at the standard. But we are working with a number of customers who are actually building their own board. It will take longer. You'll need to go through the whole sort of FPGA development process and create your own board. As I said, some customers are doing that. The way most people get started is use DevCloud, and then maybe use one of our existing boards off the shelf. And then if you find the solution works for you and you can see a path to revenue, then many people will design their own board. It's not that difficult. It's just a standard FPGA design. Okay.
Okay, great. Thanks, Duncan. Question in the chat. how is ISO C++ different from C++?
I would answer that by saying it's not really. I mean, it's just ISO is giving it the official title, and that would generally come with, the specific version. So I would say that only if you're saying ISO, then you're referring to a specific release of C++ and standard. Otherwise, I'd say they're synonymous.
Okay. There's lots of tutorials at the GitHub. How do you know where to start, what order to go in with the tutorials that are available?
There is an FPGA page that actually provides that. I will put that in the chat window. Okay.
I actually have it right here too.
You have it there.
Yeah, so you can see it. I'm going to put it in the chat window right now.
Yeah,
perfect.
Thanks.
So it kind of gives you like an idea of where to start from by keeping them in layers of tiers. So tier 1, you start, tier 2, and then tier 3. These are all the tutorials. And then when you go to the actual GitHub itself, it also has them, arranged in that order for you, so you could, decide how to begin. Yeah.
Okay. Do you have a question on the phone? I can see somebody unmuted their line.
Hello. Hi. My name is Said. I was wondering how portable is a design meant for FPGA to other, let's say, GPUs or CPUs?
Using oneAPI, I mean, the code is absolutely portable. It will move over and it will run and it will execute. What may differ is the performance. As you saw there, an example Rudy was giving, sometimes you may want to structure your code better for the architecture. I would call these micro architectural alignments, and it's usually something like that you give a loop fixed bounds rather than a variable bound. So you give a fixed bound and then say if greater than max, then exit. Little things like that may help at pipelining. And on the GPU side, there's probably some of the little tricks. Again, what you'll generally find is it's you might have a hotspot in your design and you fix that, and most of your other problems go away. And so that's coding changes. And the last thing I would say is there may be attributes that are placed in the code by the developer, and you can see them in the code. It'll say attribute, and it's part of DPC++, supported by SYCL. In fact, they're in SYCL 2020. Everything that's in DPC++, everyone does actually get fed back up and upstreamed back into the SYCL standard, so just FYI. But there are attributes in there, and those attributes may say something like, there's a standard FPGA memory. I'll put an attribute, and it's mapped to a variable. Say it's mapped to a variable X. I could put an attribute on the code that says, take that FPGA memory and split it in two, and give me double the number of ports, because that would help my throughput. Okay, so that's a way of saying this is what to do with the resources, the fixed hardware resources, and this is how to use them. So in general, they are performant, meaning you get the exact same code, the exact same functional operation. You may just get differences in the absolute performance, top performance you get, and as really showed there, you may have to go in and just tweak your design a little bit. And I would say, completely honestly, that is usually minor, I would say, code, microarchitecture, not minor, micro code architecture changes, and then maybe addressing some attributes. So that's a long answer there, but those are the two issues. Does that answer your question?
Yes, thank you very much. Another question for you guys. Can I use this flow to generate IP, let's say, for instantiation on FPGA, let's say, to instantiate within like RTL or not?
You could use today's flow and go look through the files in there and dig them out yourself. But you will be able to do that with the next release of oneAPI. In the 23.0 release, we will actually allow you to target devices. So you could actually use it to target a device and just create RTL IP and take it into Quartus.
Great. And then would I be able to specify the interfaces, let's say Avalon or Accent?
Yes.
Okay, excellent.
Yes, it allows you. So the release that's coming, and this will be, it'll be publicized around about December. I think it's December 16th or 19th is the official release date. But yeah, you will be able to target specific FPGA devices. We refer to that as an IP authoring flow. So it's oneAPI. You can use it for a full stack flow like you do today. You just plug in a card and you accelerate software. And the other flow we will support, starting with the next release, is that you can just say specify a device, and oneAPI will stop after the RTL generation stage. And then you just take your IP into Quartus. And that will all be that. That will come with documentation and training, etc. as well.
That is great.
Okay, so and that will be freely available to everyone. Just say by December 19th, it'll be part of oneAPI and Quartus.
Okay, thank you so much.
Great questions. Thank you. Another one in the chat. Are there any resources to migrate a custom OpenCL BSP to a oneAPI BSP?
There is we do have a conversion guide. There is an online conversion guide. Hopefully I can find that for you in a moment and put that in the chat. We haven't found we haven't found that to be too problematic. It's lots of little changes. None of them are in themselves major, and I think most customers have done it in a matter of hours. It just depends on how many little blocks you have. But let me find that guide and I'll put it into the chat for you. Okay.
Great. Jacob Harmon, I just had a follow up on that. I've seen resources to convert all of the OpenCL code as well as the host code to data parallel C++, but I haven't seen anything related to converting the BSP. Is the resource you're mentioning, is that specifically related to the BSP, or is it more related to the data parallel C++ conversion?
Just the data parallel C++ conversion.
Okay.
So just as soon as I find it, I'll put the link in there and I'll show everyone.
So that's not really the BSP, but is there anything specifically related to the BSP? Because it's like core, the Quartus, changes and.
Yeah, no, I thought you were talking about the code there. That was my bad. OpenCL code. An OpenCL BSP, no, that has to be modified, updated to an OFS, Open FPGA stack format. That's what oneAPI works with. I don't know the details down at that board level. I think it's basically just essentially the hardware interface. I know we have something called an OpenCL shim. Okay, maybe you could reach out. You have my name there. It's just duncan.mckay@intel.com. I'll put it in the chat. We have our developers. I know they have something. We basically call it an OpenCL shim. And basically, if we add that into the front end of an OpenCL design, it looks like a oneAPI design. It's basically just a piece of hardware or a piece of software as well, I think. So that's what we've been doing ourselves. But that takes some work and manual, and it's not something we'd put out there on the doc. But if you want to contact me, I can maybe put you in touch with some resources.
Okay, thank you very much.
Okay, and let me find that document for you.
Okay, great questions. Let's see. How much DPC++ is necessary to know before I start writing programs for FPGAs?
Do you want to go? I can go as well.
Yeah, I'd say it all boils down to what you're comfortable with, right? So we've given you like a bunch of tutorials that you could go through. I feel like once you've gone through like the first 3 tiers, you're pretty much good to go to start writing. I mean, I for one, I learn on the go, so especially if you have got C++ background, then you honestly don't even need to do too much. So it's just, a little bit of change in maybe syntax or something, but not too much. So that shouldn't deter anyone from learning. Actually, there's a question in the chat window that I think you skipped. How does multiple independent kernels be implemented and run in parallel if there's enough FPGA resources, of course? So yes, you can have multiple independent kernels inside of your DPC++ model when you're writing it, and they're going to run in parallel depending on how data passing needs are inside of your design. So the compiler is going to check to be sure that one is not dependent on the other. And then again, it's going to be dependent on how much resources you have available. You don't need to do anything extra. You just need to create those extra kernels, inside of your design, and you're good to go. That's it. Yeah.
There's another question in the chat, which looks familiar from OpenCL days. How do we support the use of networking interfaces on the hardware to connect multiple boards? And is the host aware of that somehow? Being able to implement the pipe for kernel to kernel transfers over a network interface. The use of networking interfaces on the hardware.
Off the top of my head, I don't know the answer to that one. I know we have that feature. I just don't know if it's in the software. I apologize. It's not something I see often, so it's not in the front of my mind. Really, do you have any idea?
No, I was gonna say the same thing. Like, I'm not sure of networking interfaces, but for pipe to pipe, yes, you can actually do pipe to pipe kind of movement from one kernel to another kernel. You could do that inside of your, I know it as part of writing it in the software, and that's going to be implemented for you in the hardware, but how it kind of boils down to the networking interfaces, I'm not sure of that answer at this moment. Yeah.
Okay.
Yeah, I
question
think
on the phone?
I was going to anyway.
Oh, go ahead, Duncan.
No, please go ahead. I think we already covered everything.
Oh, no, I thought somebody was going to ask something on the phone.
Hello. I have a question here if you guys don't mind.
Yes, go ahead.
How easy would it be to call one of these data parallel C++ codes implemented on a FPGA from a standard C program? Like, basically, can I build a library of different, let's say, kernels and call them externally using a C function?
Off the top of my head, I don't see a problem with that. I mean, it's just standard C. To touch on a question that someone else asked there earlier on, how difficult it is for data parallel C++, it's basically just C++, everyone. What it does have is some extensions at the top that will define the concept of a queue. It will define the concept of buffers. You can make the inputs to your C code define them as input buffers or output buffers or bidirectional buffers. Or alternatively, you could define all your inputs as long as it's a shared memory. It's shared with the similar variables in the level above your kernel. And that's about it. That's about the only add that DCP++ adds, or SYCL really adds. It's just those concepts of a queue and buffers at the top level. The rest of it is C++ 17. So anything you're able to do, you should be able to do the same thing. The only thing I wouldn't say is if you're going to dynamically swap these memories around inside a kernel that's going to be synthesized, I'm not sure how that would work. I don't know if anyone's done that. But if it's C++ and it's supported by C++, it should be possible. The only thing I can think it would stop it if it's unsynthesizable. And by that, I mean, you can create C code, for example, with virtual functions. Well, a function must either be real or not. It can't, in hardware, it can't be virtual. So that's unsynthesizable. So as long as your libraries are synthesizable, I shouldn't see a problem, but I haven't seen this specific example. So I would, if I was you, I'd proceed forward confidently. I would. I don't see any problem that stops it at the moment. But I could be wrong. Okay.
All right. Another question in the chat. How about partial reconfiguration? Can kernels be dynamically switched?
I don't think so. Ruri, do you know the answer to that one?
Yeah, off the top, I'm thinking like switching what sense? Because no, so far I've not stumbled on any kind of switching between kernels. So, but maybe you mean it in another different dimension. I don't know. Nah,
I think that was kind of an OpenCL thing, right? Where you could swap out kernels.
Just going to say, I think it is supported in terms of OpenCL behavior. So that if you've got the same kernel that must run multiple times, or a couple of kernels that have to be run, that's all part of the OpenCL language. That should be supported. In if you're talking about partial reconfiguration, as in, dynamically swap into a different design, I'm not sure about that. So what I'm saying here is, if you've got a kernel and say it's a large kernel, we call it kernel A, then like OpenCL, it has to be executed multiple times in hardware. You transfer over part of it, and you take it back, you transfer over some of it. That's supported. If you're dynamically trying to swap kernel A and B, I'm not sure. I need to go check. That may not be supported. But standard OpenCL behavior, as in moving kernels and dealing with kernels in terms of ND ranges, that shouldn't be a problem. I don't think anything should be lost from OpenCL behavior. And I may be personally thinking of a different way of dynamically swapping around kernels. But all that should be supported. I don't think you should have any problems with that. Anything that was supported in OpenCL should be the same.
Okay.
Okay.
Got about 5 minutes left, so get your questions in. We still got some more. Do we plan to support the host being the FPGA ARM HPS in the IP? I think this is kind of two questions. Let's do the first one. First question first. Supporting the HPS for the host.
That I don't think so. So in this model where we use what I call the full stack flow, everyone, where you plug in a card or basically a CPU, and then you just run oneAPI. That's what I call a full stack flow. And that flow we don't see at the moment the ARM taking over. And that flow, the accelerator is a card that's plugged into a chassis in a data center. Now, if people start building cards that are dominated by ARM processors, yeah, it should be easy enough for us to support that flow. But at the moment, we don't see many people doing that. Now, I think there was a second part to your question there, Steve.
Yeah, in the IP authoring flow, do users get a library or API custom for the IP that's auto-generated?
Okay, so I'll take that question next. Let me go back to the first part of the ARM. In our IP authoring flow that I spoke about, I do see us working with the ARM processor. So I do see us using the ARM processor and integrating it, but in the IP authoring flow, and not having the ARM replace the Xeon effectively is the answer to that question. So in your second question there, Stephen, I just asked you because it was related. Can you repeat that again?
In the IP authoring flow, do users get a library or API that's custom for the IP that's auto-generated?
You don't get so much get an API. In the IP authoring flow, what you'll get is all the output RTL files. So for anyone who's familiar with hardware design, you'll know what that is. For anyone who's not, so when oneAPI runs, as Rudy was explaining earlier, and you can use it in software emulation. You just compile like regular code. When you second time when you're running it and you're actually generating the reports, during that phase, oneAPI is actually building a hardware model under the hood, and those reports show you that hardware model. Now, in the standard flow, you would use, if you're happy with that hardware model, you would just go on and then down and run your card. In the IP authoring flow, you would actually stop at that point and just take all those RTL files. So that is essentially your API. You take these manual files and you take them over to Quartus and you would integrate them yourself. So does that answer your question?
Hi, Duncan. This is Benor. Yeah, kind of, because at the end, if you're generating an IP and the next phase, you need to re-architecture all the driver and whatever software in order to use it. It just makes the usability much more complicated, right?
Yeah. So I would say in the first release, in terms of an API, if you want to call it that, we will just be producing the RTL or the hardware model. In the next few releases, we would produce the software driver files that go with that. So that if you had actually produced a piece of IP that required a slave interface or an AXI Lite interface, we would produce the software driver files that go with that. So you could just take that and incorporate it into your software and automatically know how to, as automatic as possible. Hopefully with just some header file definitions, you should be able to just include that into your ARM software and write to the IP.
Okay, thanks. And another question, if I have a minute. So
1 minute.
is supporting somehow the ability to have DMA engines in the FPGA, pulling and pushing data rather than the host doing all the data movement?
I don't know. I mean, if that makes it more efficient and there's a way to do that, yeah. I mean, I haven't seen a problem with that at the moment, or a reason why not to let the CPU just DMA things over.
If there is a way to DMA from the CPU at the end, if you're just kicking off a kernel which needs data from host memory, pull it direct rather than having the host push data.
Yeah. So later on, I mean, what you're seeing with Intel at the moment in the RTL domain on the hardware side, we're introducing CXL. So to go more, I would say probably a year or more down the line, we'll introduce CXL features into oneAPI. So that there should be more easy. It should be easier then to have cache coherent memories and for the FPGA to directly access the host memory and improve that.
Okay, thanks, Duncan.
Okay, well, those features will come. I think you'll see those features implement first in hardware until the industry is quite good that we execute well, and then we'll automate that through oneAPI. Okay, sorry, Stephen.
No problem. I think we had some great questions, and I think this was a fantastic session. So with that, we are out of time. So thank you all for attending. I have placed a feedback survey link in the chat. We'd really appreciate it if you would click that and just answer a couple of short questions about what you thought about the session and ideas for upcoming sessions. We'd always like to hear your feedback. You'll also get an email within the week with the same link that's going to be sent out for people who didn't connect up. But that's it. So we're going to stop the recording in a moment, and we'll close the Teams meeting. So thank you all for attending. We're taking off Ask an Expert in December, but we'll be back in January. So look for invitations to our next session coming up. So thank you all for attending.
Thank you, Steve. Thank you, everyone.